Is my screen visible here?
Yeah, it's visible.
Yeah, okay. Yeah, so let's begin. So this discussion will be on designing exponential algorithms using dynamic programming. So what I mean here by exponential algorithms is like those who like I hope most of you might know what dynamic programming is. But those algorithms, like the problems which were targeted, were mostly solvable in polynomial time. Okay, but there are problems which are NP hard, means they can't be solved in polynomial time. But still, for real life application, say an algorithm of 2 to the power n is not bad when compared to say n to the power n. Okay, let me write here. So if you have 2 to the power n and n to the power n, then say there are many applications where, especially in our computer itself, where n is 30. Okay, so 2 to the power 30 is a small number for computer, but 30 to the power 30 is a very huge number. So the question is like, can we remove this n part and replace it by a constant c, some c to the power n? Okay. So n to the power n is basically brute force. You try each and every method, and then you try to get some solution to the problem. But c to the power n is something more than that. And basically, as you know, dynamic programming is a very clever brute forcing. Like you avoid repeated small instances so that you can convert this running time to some constant to the power n. Yeah, so that's the basic idea behind the topic today. So I'll take up three classical problems of theoretical computer science, like which are like very well studied. You'll find lots of research papers on them. So I thought like explaining dynamic programming via these problems will be quite helpful. Yeah, so let me begin. So first we look at traveling salesman problem. Like this is one of the well-known problems here. So yeah. So what is our aim here? So we are given a graph. Okay. So between each node in the graph, we have an edge, and each edge has a weight. Okay. So for this particular edge here, we have a weight 1. Okay. And similarly, for an edge between these two nodes, we have a weight of 2. Okay. So we have this graph and edges and weights on it. Okay. So what our aim is? Our aim is to find a cycle containing all the vertices. Uh, so like not exactly cycle. I would say let's mark this node here. Okay. So what we want to start. Say suppose like let me give in terms of real life example. Suppose each of this is a city. Okay, and there are roads connecting to each and every city, and the length of the like you weight of an edge, you can consider it to be distance between two cities. Okay, so what you want to do, you want to start at this city, travel all the cities, and then come back to the original city. So that's your aim, and you want to do it by covering as less distance as possible. So that's the aim of this problem. So one possible route can be you start here, you go here, then you go here, then you come to this city and then return back here. Okay. So this is one possible way. So can someone tell what is the length of this tour? Basically, length of the distance covered. Basically, I'll make the image clear. Wait. Yeah. Can someone tell me what is the length of this path which is being covered here?
7 units.
Let me see. It should be 6, right? Like one,
Yeah, it is
then
6
two.
units.
No, it's 7. He told it correct only. Sorry, it's my bad. Let me check once more. Uh, 1 plus 1, 2, 2 plus 2, 4, 1, 7. Yeah, 7 units. Yeah. 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 So it's 7 units. But the question is, can you do better than this? So obviously there is one more part, like one more cycle. You start here, you go like this, and you come back. So this is the path, and your length of the edges is 5. Sum of the length of the edges is 5. So your optimal solution, optimal answer is 5 basically. So this is the basic crux of this traveling salesman problem. So okay. So what we want to do is that we want to solve this problem via a dynamic programming solution. Okay. So ideally, the problems like okay, so the problems which you might have dealt, the like how they explain dynamic programming. Can someone from the audience say like how like what way you think? What do you think? What dynamic programming is? Like, can someone tell from the audience? Like, just say what dynamic programming is actually.
You can break a problem into its subparts, and it turns out those subparts have the same structure as the original problem. So basically, you can store the results of smaller instances of those problems and reuse those results to get the result for a bigger value.
Yeah, sure. Yeah. So basically, that's what they sort of tell you while they teach you dynamic programming. But like, sort of, it's not exactly what they should be telling. Actually, what they should be telling is like you convert your original problem into some other problem whose solution will be a solution for our problem too, and that for that particular problem we divide it into small instances which whose answers can be clubbed to get the answer for the bigger instance. So that's what we should actually do, like directly like breaking, suppose you try to break this problem into smaller parts, will not make any sense actually. So we should cleverly sort of choose our problem instance, like the problem definition, so that the answer for this is answer for our this problem also. So let's see what can be such a formulation of the problem. So basically, okay, just a second. Okay, yeah. So basically, whenever we try to design a dynamic programming, basically we have a table. Okay, it might contain some arguments, and basically we want to store the values, and we want to compute this table. Okay, so basically, if you have some A, B, C, or say D because I have used only C there. So basically, this is some C, and these are arguments of that table. Like you have a table, and these are the you can say this is a cell of a table. Okay, so so basically, you have to define properly what this actually means with respect to your problem. Okay, so this is what your aim should be roughly. So yeah. So basically, for this particular problem, let's see how we can frame our problem cell, like the dynamic programming table. Okay. So let me just go to full screen. It will be better. Yeah. So, so let us assume that the set of vertices in the graph is C1 to Cn. Okay. So, what our dynamic programming table does, it computes something called OPT S comma Ci. Okay. This is the table which we are trying to compute. So, let me tell what does this S and Ci stand for. So, just without any like loss of generality, let's assume that this starting vertex is C1. Okay, that is the starting vertex, And so S is basically a non-empty subset of this particular set, like which is the remaining set of elements. Okay, and Ci is basically some element in S. So that's what S and Ci mean. And what this OPT SCI means is that, let me explain with help of a diagram here. So what we have OPT, we have OPT S, we have this thing. Yeah, we have this thing. So what does this mean? Suppose we have C1 and we have C2, C3 up to so on and Ci. So what this means is that we start from C1, we cover the vertices which is present in the set S, and then we finish it with Ci. And what this OPT, this particular cell covers, what this particular cell tells is that for all possible such tours, like if you start from C1 and you end up at Ci, covering all the vertices of S, what is the least possible path, like least possible length of the path? So suppose the least possible length of this path starting from C1 to Ci is 7. Then our OPT SCI is 7. So this is basically the definition of the problem instance which we are trying to look at. So this is the basically the definition which we should be looking at. And as you can see, this subproblem is nowhere related to the subproblem which we're like the original problem which we're discussing. Like the original problem involved starting from here, covering all the vertices and then returning to the original vertex. Okay, so that was the original problem, but we modified the problem and we made it into, we start at C1, we cover all the problems in this set S, and we end up at Ci. So that's what we did. Okay, so can someone tell me then, suppose I have computed this these values. I have computed all possible values of this table. Okay, for all possible set S and for all possible Ci. So can someone tell me how using this I will find an answer for this particular problem here? Can someone from the audience try? I'll give 5 minutes. You can sit. You can think. Or if you have anything, any doubt till now, you can ask me actually. I'll keep this slide open in case you want to see, have a look, have a read at this properly. What is the exact subproblem in case? And then we'll discuss the solution. So is it clear till now? Can someone confirm?
Doubt here that
Yeah.
in this problem we are telling that we need to visit all the vertices in S. We'll start from C1, we'll visit all the vertices in S and we'll end in Ci.
Yeah.
Are we allowed to, in this tour, are we allowed to go outside the set S? We have to stay within S only.
No, we should be staying inside us only.
Okay.
Could someone get how can we find like how can we solve the problem of traveling salesman if we suppose we found all the values of this particular table here, OPTSCI. Would anyone like to try?
We can set the original S to the original set, and for each vertex we can look at the minimum weight from that vertex to C1, and then from there we can easily do that.
So basically what you mean is, let me write it more formally here. So basically you mean this thing, minimum of, like basically S is the S is basically
Whole
C2
set.
to Cn. Yeah, whole set, not the
Yeah.
subsets. Basically from C2 to Cn.
And for each
And
vertex,
yeah, basically you want to do minimum of, sorry, S SCI plus the distance between C1 and CI.
yeah, if there is any vertex at all, if there is any edge at all.
Yeah, there will be edge actually. Like it's considered to be like all possible pairs will have an edge. That you can be
Oh,
rest assured. Otherwise, you can, if they don't have any edge, you can keep the weight as infinity.
yeah.
Yeah. So this is basically, this particular expression will give me the solution to the traveling salesman problem. So this basically means the distance between C1 and Ci because we need to return to the original solution. So basically what Manideep meant was, you start from C1, you cover all the vertices and you end up at Ci, but you need to return from Ci to C1. So you take that additional edge, you add this, and you do this for every vertex basically. Because at the end, when we are doing this tour here, one of the vertex must precede the first vertex, obviously. So that's why for one of the CI, we'll definitely get an optimal solution. So that's what is the overall logic behind this dynamic program. So you saw how we converted our traveling salesman problem to a very similar problem. Okay, the problems are not drastically different, but they're quite similar. We converted into a similar problem, and then we'll see how we'll solve that problem now using dynamic programming. But suppose if we solve that problem, then we can go back and solve our original instance. Yeah. So let's see the recursive equation, which is quite simple. Like I could have asked you, but yeah, I'll just tell you. Uh, so basically, yeah. So let me. Yeah. So basically, it's quite similar to the original like overall problem how we did. So what you have OPT SCI. Okay, you want to calculate this. So obviously some vertex must be before this. Like if we have a path from C1 to CI, then there must be some other vertex which was just before CI. So you remove Ci from S and you consider a vertex Cj and you compute that OPT, and then you add the edge between Cj and Ci. Okay. So it will be better if I explain using a diagram. So basically what you want to calculate. You want to calculate the sort of a shortest path from C1 to Ci, covering all the vertices in the set S. Okay. So observe that in the optimal solution, there will be an edge, there will be a vertex Cj, which is just before Ci. Okay. So, so what we do, so obviously one more thing you observe, that this, this should be optimal. This should be an optimal solution from C1 to Cj. If it is not optimal, then we can replace it with optimal and we'll get even a further smaller path. So that's why the the path from C1 to Cj should be optimal. So that's why what we do, we calculate OPT S minus CI because we are excluding CI, and it should end at CJ. Okay. So this is what we want to calculate. Okay. So this is what we want to calculate. Plus the answer to the original OPT problem would be we have to add the distance between this and this edge. Cj and Ci. So we add that distance there. I just represent it by D. It's distance between Cj and Ci. But the main question is we don't know what that Cj will be. So what we do, we take all possible Cj values. Like you take all the elements in S and you assume that particular vertex is Cj, and you calculate the values and then you choose the minimum value among them. So this is what is being done here. So you take OPT SCI, you calculate OPT S minus Ci, comma Cj plus distance between them. But since you don't know what is that Cj, which will give optimal solutions, you do this for all possible Cj and you compute the minimum value. So this is the recursive equation. Base case is quite simple. Like if you have just one city in S, which is Ci, then obviously it's nothing but the distance between C1 and Ci. So this is the recursive equation. And as Manideep told, like this how we calculate the OPT value, like optimal solution for traveling salesman problem. Okay. So I hope it's clear till now. So if it's not clear, anyone can stop me and ask. Does anyone has any query till now, or is it clear till now? Can someone confirm either of them?
I have one question.
Yeah.
That is, while visiting all the cities, can I visit one city more than once?
Uh, you think logically, will you ever get greater, like the distance are not negative in first place, they are all positive. So will you get any advantage by repeating a city?
Yes, but if I don't repeat a path, it might be possible that I have a lower weighted
But
paths coming.
ideally we won't want that thing to happen. We won't want any city to get repeated.
Okay.
Yeah, but just think whether will you get any advantage by repeating a city. At least for the real life scenarios, I don't think you'll get any advantage. The real life scenarios are Euclidean stuff, like you have triangular inequality. So at least for those type of scenario, I don't think you'll get any kind of advantage. But this works for any kind of distances, this particular dynamic programming. So, okay, so I hope it's clear. So the only thing which is left to see, yeah, ask.
Means that question that she was asking. So in this case, like if we assume that some city is repeated, so suppose
Yeah.
let's say vertex V is repeated. So that means we have a
Yeah.
path from C1 to V, and then again
Yeah.
from V to again we are coming, and then from V to CI we are going. So this
Yeah,
is the case
basically,
when.
yeah, it's coming here and then it's going here and then it's going here, basically.
Yeah. So we can just remove that path between V to V. So it will result in a
Yeah,
smaller unit.
that only I wanted to say. It won't be of any use. You are basically repeating this extra portion. Hello?
Yeah, okay. Yes, yes.
Yeah, that's what he was telling. Yeah. So in terms of original answer to the optimal value, it won't be of any use because this part is there actually. Yeah. So, but for non-Euclidean distances, you have to be more careful actually. So, but it's of no harm for us to assume that no vertices is repeated. That's of that there's no harm in assuming that because in the original like the problem TSP problem, no vertex will be repeated. Yeah. So uh, yeah. So So basically, okay, so we have seen everything. The only thing which is left to be seen is what is the time complexity. Okay, so there are very formal methods to calculate time complexity. I'll tell you a very simple method. Like in book, they do all the algebra, summation, this, that. I'll tell you simple technique. So can someone tell me what is the total number of cells which is possible? Like the answer is there, but can someone explain me what is the total number of cells in the DP table which we are calculating, which is possible? Hello? It's quite simple. Can someone try?
Total number of cells are n, so the number of elements in the power set of S will be 2 to the power n, and
Yeah,
there are n vertices, so number of elements in power set into the number of
yeah,
vertices, so it will be 2
yeah,
power n into.
yeah, yeah. You're absolutely right. So it will be 2 power n into n, and we spend in each cell order n time. It's here because we are just like this. If this minimum is not a order one operation, it's order n operation because you are taking minimum over n values. So that's why you will be spending at each cell order n. So you just multiply it. So you'll get 2 to the power n into n square. So this is the time complexity for our problem. Order 2 to the power n into n square. So I hope it's clear. So I'll move to the next problem, which is
I have a
another.
doubt.
Yeah, yeah, yeah. Ask.
How is the time spent that each cell is O n? I didn't understand.
Okay. Okay. I forgot to tell one thing. Okay, so in dynamic programming, we basically I'm assuming that you go from bottom to top. Means by bottom to top, I mean that for smaller sizes of S, assume that you have already computed. Okay, the values. Okay, so using them, you now try to compute the values of OPT S comma CI. Okay, you go from you start from the base case and you start building up the solution. Okay, so basically the standard assumption is you assume that for smaller sets of S, we have computed the solution. Okay. Then how much time will it take to compute this particular thing? So this OPT is already there in our memory. Okay. So you just call from the memory and add the distance. So this is order one. Okay. So one step. And you have to do these steps at most n times because there can be at most n elements in set S. So you do this for n times. So in order to calculate OPT S comma CI, you are spending n number of steps. That's why you have this particular thing here. Is it clear?
Yeah,
Yeah,
yes, it's clear.
yeah. So I hope it's fine then. Then we'll move to the next problem. So this is one more classical problem in graph theory. So so this is bookish definition. Let me go to take help of this thing. Open a new thing because the old one is spoiled. You guys can also use this in future. Like this is a very good drawing app. I don't have any pen also. I'm drawing it using mouse, so it's quite convenient to draw using this particular drawing board. Yeah. So what we have? Suppose we have a graph. So we have a graph. Okay. So we have to color the vertices of this graph. Okay. So suppose we have color the vertices. Suppose we color it with green. Okay. So we can color them with any color, but the only constant sort of we have is that if there is an edge between two vertices, then those two vertices should not have the same color. Okay. So that this is the only constant which has been imposed on the coloring. Okay. So the question is, what is the minimum number of colors which you need to color this graph? Okay. So for this problem, okay, so there is a solution where you use three colors. Okay. Okay. Where we use three colors. Can someone tell whether we can use two colors and color this or not?
So in that triangle, at least three colors will be required.
Yeah, we'll require three colors. The reason being is that, see here, this particular thing here. So this is connected to this. So this both should have different color. This is connected to this. So this both should have different color. And then this is connected to this. So this both should have different color. So basically these three should mutually, they should have different colors. So at least we'll require three. And we gave a coloring which requires three, which we gave a coloring where we used exactly three colors. So it means that the minimum number of colors is three. Okay. So this number we call it as chromatic number. So so we call it as chromatic number here. So the aim is to compute chromatic number of the graph, and it's not that easy as you think. This problem is also NP hard. This problem has huge applications. Like even even to decide even to decide whether you can color a graph using three colors or not, even that is also NP hard. So even that is also a very tough problem. Okay. So this is a question in our hand. So yeah. Yeah. So this is a question in our hand. So we look at the dynamic programming which will be used. Okay. So for this, as someone told at the start of the talk, in this case, the smaller problem is the exact replica of the original problem. Okay. So we have OPTX. Okay. So what does OPTX means? It means that we want to find chromatic number on the induced subgraph of X on X. What do I mean by induced subgraph? It means that you only you remove all the vertices which is not present in set X. You remove it from the graph G. The graph which is remaining is called induced subgraph on set X. Okay. So this is what I mean by induced subgraph. Let me move once. So just one small example. So you have yeah. Suppose this is my graph and my set X contains this, this and this. Then so the set X contains these three vertices. Then the induced subgraph is on X is this thing. So this is the induced subgraph on X. So the OPTX denotes the chromatic number of the induced subgraph on X. So obviously the chromatic number of the graph is nothing but OPTV, where V is the set of vertices, because the induced subgraph on V is nothing but the graph itself. So this is the like this will give me the solution to the original problem. Okay. So now let's see how can we compute OPTX. Okay. So okay. So how many of you know what independent set is? Does anyone is there anyone who doesn't know what an independent set is here? Tell either yes or no, anyone. Can someone tell like whether they know independent set or not? So that if they don't know, I can tell what it is. Okay, then I'll just explain it quickly. So basically, independent set is a set of vertices which don't have an edge between them in the graph G. So if you have a graph G, then independent set is a set of vertices which don't have an edge between them. And an independent set is said to be maximal. It's said to be maximal if we can't add an vertex to it which doesn't have and may create a larger independent set. So that's what we mean by maximal. It's not maximum, it's maximal. So you can't add one more node and make it still keep it as independent set. So this is what I mean by in maximal independent set. So here they have here it's written that OPTX is 1 plus OPTX minus I. I is independence maximal independent set. Let me explain what do they mean by this. So I'll just rewrite it again. Okay, 1 plus. So doing minimum over all in maximum independent set. So what basically so what let so basically what's happening here? You you take a maximal independent set, okay, and then you remove it from this set X. You add one to it, and you take minimum. You take minimum over all such possible I. Okay, which is what they're doing here. But the main question is, what? Why will it work? Basically, like why is OPTX 1 plus minimum of OPTX minus I, where I is maximal independent set of the induced subgraph on X? Why is it the case? Can someone from the audience try to give an intuition why this should be the case?
Like if they are not connected, then they can be colored using the same color.
Yeah, yeah, that's the point. So, so basically, in the optimal solution, the the colors which have been used, if you suppose we used red color, okay, Suppose we use red color here. So since this is a coloring of a graph, and I told that no two vertices which have an edge between them have the same color, it means that the set of vertices, say, which have color red is an independent set. Okay. Yeah. So it's an independent set, and you can assume that this is a maximal independent set. Otherwise, we can rearrange the coloring, and you can bring some vertex which was not originally red. You can color it red. So, okay, let me explain it properly. Okay. So what I mean is, suppose in optimal solution, there was a color, there was a vertex which doesn't have any edge with them. Okay. And it was colored with some different color. Okay. So what I can do, I can just change its color to red. I can just change its color to red, and still it will remain a proper coloring. Can anyone give me the reason why still it will remain a proper coloring?
Because it doesn't have any edge with the red vertices.
Yeah. And will it still be optimal solution? I mean, which uses least number of colors?
Yes, because we are decreasing the number of colors.
We are not exactly not decreasing, but we just changed the color to one of the existing colors only. Basically, we didn't use any new color. So that's why,
Yes.
yeah. So you can make such modification. Okay. You can make such modifications and ensure that at least, sorry. Yeah. So you can ensure that one of the colors, obviously the colors will form an independent set, is maximal. Okay. So you can sort of assume that there will exist one color which form a maximal independent set. Okay. So that's why we can just do 1 plus OPT x minus I. So this is what you can do. So you know one color will be maximal. You remove that maximal set. One color has already been dedicated for it. So you add one. And for the remaining graph, you calculate the chromatic number. So if you add them, then you'll get the chromatic number for the original graph. But the question is, we don't know which maximal set it is. Like if I'm telling that, okay, red color is maximal independent, I don't know which maximal set it is. So simple, you just brute force over all possible maximal independent sets. So that's why it's minimum of this thing actually. So it's minimum of that thing. And you add one. So that in that fashion, you'll get OPTX. So is it clear why this equation holds true? This particular equation here. Is it clear? I hope it's fine then. Uh, yeah. So I hope it's clear then. So I'll proceed towards the calculation of running time. Okay. So
I
for
have
this
one
case,
doubt.
yeah, ask.
I understood that it is the subproblem of the original problem, but how are we using this result to solve the original problem? I mean, if the optimal solution is OPTV only, then is it just a method, or are we using the solution of the subproblems to solve the original problem?
Yeah, we are using, right? We are calculating the smaller sets, and at the end we'll calculate OPT. How will you calculate OPT? OPTV is equal to 1 plus OPTV minus I, where I is maximal independent set of my graph G. And you, since you have calculated OPT for smaller sets, then you can calculate OPT for the original set of vertices.
Okay, okay, I got it.
Yeah, yeah, yeah. So, can someone tell me? Okay, so the earlier way how we calculated the time complexity won't be of that much use now. Okay, so we have to go to some different sort of like analysis, which is just simple. Okay, so okay, so can someone tell me for a set X of size I, how many independent sets can be there? So let me write it here. So you have a set X which has I elements. Okay. So how many independent sets can that set X have? At most, how many sets can it have? Independence, independence or just independent won't be of that much of a difference. It's quite simple. Can someone tell?
At least I and at most 2 power I.
Yeah, at least I, that's correct. And at most 2 to the power I. So that's the answer I was looking for, 2 to the power I. Okay. And so basically for each cell, we are spending 2 to the power I, like each cell where X has a size I. We are spending 2 to the power I sort of time. Okay. So there are n choose I possible number of set X. Like what is the total number of like what is the total number of set X, which is a subset V of subset of V such that its size is I. It's n choose I. Because you have n elements in V and you have to choose I elements from it to create the set X. So for n choose I number of sets, we are spending 2 to the power I. And the set of sizes of the set can vary from 1 to n. So you do this summation, you will get 3 to the power n. Okay. So this is what we get. So the running time is 3 to the power n. So to this problem, I wanted to give one more thing, like why do we okay, so independent of this, people do some other kind of research. So what is the use of those kind of research? Like what is the use of those kind of research unless we can use them to improve our this particular result? This is quite naive actually. It's 3 to the power n. Like sort of you were doing almost brute force and got 3 to the power n. When you do sort of research or anything, you want to improve it. So the question is, how can you improve it? So the do you change the DP? Maybe you can change the DP, get a different type of DP and get a faster running time. Or do you sort of analyze this thing? So the question I asked before was, what is the number of independent sets which we have? And you can see the answer was heavily dependent on it, 2 to the power I. So this is binomial, right? You just, what does this become? 1 plus 2 to the power I n. That's the summation which we do. what the question is it really 2 to the power I? The number of maximal independent sets. Turns out that it's not. Actually, it's 3 to the power I by 3. That's a huge research paper actually. One of the standing achievements. I'm asking. I asked where I is number of maximal independent sets. For just independent sets, yes, we have 2 to the power n independent sets. Like if we have a set of size n, but if we want maximal I mean that you cannot add one more vertex and make it an independent set. In that case, the number of maximal number of independent sets is 3 to the power I by 3. Okay. Basically it's cube root of 3. What is cube root of 3? I forgot. Was it 1.7? I don't know. Yeah, it was around 1.7. So it is 1.7 to the power I, not 1.7. What was cube root of 3? Wait. It's roughly 1.43 as far as I remember. Yeah, it's 1.44, not 1.7. Sorry. So 1.44. So you saw that this is purely a graph theory based result. It has nothing to do with algorithm. It is purely a graph theory based result. And later algorithm wise also they showed that we can list all those independent sets in the same time, like order 3 to the power I by 3. So this is an improvement. So as such we didn't change our algorithm. What we changed was our analysis basically. So we use this here. Earlier we had 2 to the power I. We now make it 3 to the power I by 3 and you do the summation and it becomes 2.44 to the power n. So is it clear what I told till now? Is it clear? Or does anyone has any queries regarding it? It's clear, right? Okay. So this is the last problem which we'll discuss. So let me open one more tab again. And this last one, I'll give brief overview. Rest I'll leave it to you guys to actually sit and formulate stuff. But I'll just give a brief overview. Okay. 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 So how many of you have a fair idea of what directed graphs are? Like, I hope you should know what directed graphs are. Till now, we were dealing with undirected graphs, means the edges don't have any direction. Okay. So now our edges have a direction. And our graph is said to be cyclic if we have a directed cycle, okay, of this type. And it's said to be acyclic if we don't have a directed cycle. So this is not a directed cycle, which I'm drawing here, right side, because you should start here and you must be able to return here, which is not possible. So this is acyclic, this is cyclic. So the question is, what is the minimum number of edges which you must remove to make a graph acyclic? Okay, so this is the question. So at least, did you get the question? Is the question statement clear? You can just have a look at this, like this is a bookish definition. I don't want it to be like professors who just read the statements and go away. So is it clear? Can someone give an yes? I'll take it as yes then. So okay. So I'll not tell. I'll just okay. So what should I do with this problem? Already it's 8. Okay. Uh, okay. So maybe some of you might know this thing. Some of you might not know. Still, I'll tell it. Okay. So this problem actually yesterday I sat and solved. So let's see if any one of you can at least try to tell me the intuition. How can we create dynamic programming table? And I'll not tell the exact solution. I'll give the slides, but don't see the slides. Try to solve the question on your own, and then you can open the slides and you can see. So we'll discuss. We can discuss orally. How can we formulate the dynamic programming table? Like that, what can be the problem we should be focusing on? But before that, we must have a look at this. So this is an important property of graph. We say that a graph is acyclic if and only if it has a topological ordering. So what we mean by topological ordering, basically you start assigning numbers to the vertices. Okay. And for any edge in the graph from this vertex to this vertex, the number of this vertex should be smaller than number of this vertex. So such a numbering is called topological ordering. So I hope if it's clear what I mean by topological ordering. So I'll not even okay. Let me not discuss the dynamic programming subproblem. But what I'll tell you is that you have to make use of this fact. Okay. You have to make use of this fact and try to come up with a dynamic programming table. Okay. So better I'll stop the discussion here. You can sort of take it as a challenge. Better I'll upload the slides tomorrow. Okay. Somewhere in the evening so that at least you try for some time and try to come up with a solution. If someone has any doubt regarding topological ordering, please ask me. What is topological ordering? It's standard stuff. If you guys don't have any doubt, then if you guys have any general doubt, you can ask me. I'll stop sharing. Yeah, and I'll stop the recording also.